Hello everyone. Today we will start 7th lecture, and 7th lecture would be on driving force del G. And initially we will consider single component system, and that too we will considering liquid to solid transformation. This is a very comparatively simple derivation, and later on we will go into the solid to solid transformation, which will be a bit more complicated. And when we try to take the single component, it is also simple compared to the system when we will take binary system, where there will be two components, and in most of the practical applications we deal with alloys which are binary or ternary, or even the alloy might contain a number of elements, more than 4 or 5 elements. So, but before going into the complications, let us handle a simple condition and where we will take single component. And you must be wondering that though we will be talking about heat treatments of steel as well as aluminum alloys, so then why are we considering liquid to solid transformation? First of all, it gives an idea that what could be the way to find out del G in a very crude manner, I would say, which is I would say a very simple manner. But at the same time, liquid to solid transformation is useful in one of the structures which is known as a glass. So, glass is a kind of structure which is also in the form of solid, but interestingly the structure is random. That means in 3 dimension it does not have a long range periodicity. So, that kind of structure we call it glass, and in many of our practical applications we do use glass. One of the classic examples is window glass. So, that does not have a periodicity, long range periodicity. So, there also we get a random structure to a very periodic structure, which we call it crystal, and that time it is called crystallization of glass. And mostly in many of those polymers we do get glassy polymers, and at the same time we do get a mixture of crystal and glass for polymer, which enhances the properties. So, those cases this will be a very vital transformation mechanism, and at the same time many of those glasses we do get in metals, we call them metallic glass. One of the famous metallic glass is fine met. Fine met, this is one of those iron based metallic glass which has fantastic soft magnetic properties. So, there also we try to get a glass which is in solid, and later on we try to modify its structure by crystallizing, so that to improve its magnetic response, soft magnetic response. So, those cases this particular transformation would be very critical. And even in case of cast iron, when we do consider casting of liquid metal, that time also the solid liquid transformation or liquid to solid transformation are depending on how we carry out that melting, that solidification operation, the structure do vary, and that time we do get a difference in properties. So, these particular transformation from engineering perspective is very critical. So, one is it gives a simple expression for del G, and that to a single component system, and also it has engineering importance, and that too later on we will see that heat treatment does play a huge role while looking at this particular transformation. Now, we have seen from our previous lectures that in case of solid liquid transformation, if we try to plot G versus T for a single component system, pressure constant, and let us consider 1 atmosphere. So, we get this kind of graph. So, this is my G S, this is my G L, and this is my T M. And we need to find out at any temperature less than T M, let us say we try to find out what is my free energy difference if we can quantify this G. So, this is my temperature where we like to find out, this is my temperature axis, this is the temperature where I would like to find out what is my free energy difference. And as we know that in order to calculate the difference in state function in thermodynamics like G, S or H, we have one experimentally determined value which is Cp, which is heat capacity. Heat capacity. Now, if we can find out the Cp of solid as well as Cp of liquid, we can easily determine what could be the value of del H liquid to solid, del S liquid to solid, and finally, we can get del G liquid to solid equal to del H liquid to solid minus T del S liquid to solid. So, this simple formula we can use, and here now we have to find out how we can get this value as well as this value. Let us assume that we do have calculated values of these two parameters. So, now if we try to see as a function of temperature, if we try to find H enthalpy value for solid and liquid. Now, at temperature less than, let us say this is my Tm, at less than Tm and this is 0 K, let us say at this some temperature, I can easily find out the Cp of solid, and accordingly I can find out Cp dt equal to Th. So, now there I can have H plot. Now, at Tm, beyond Tm, I will get liquid and that liquid is stable. So, I can calculate the Cp of liquid and then I can find out the H of liquid, and this is H of solid. And as we know, the melting is first degree transformation, first order transformation, and that time there would be a sharp drop which we call it as enthalpy of melting. Now, this Cp, from this we can get Cp information, liquid, this is Cp of solid. Now, if we extend this line, assuming that this is following this track, and somehow because of some mechanism, if we can find out the experimental Cp, so then at any temperature, let us say at this temperature, I simply find out del H, which is the difference between liquid and solid. So, that means this is, let us say A, this is B, this is C, this is D, and this is my enthalpy line. Then this I can easily calculate at T. Now, when we try to calculate this value, since we know this value, this we can calculate from a DSC, simple DSC route, which is called differential scanning calorimetry. Calorimetry, which actually plots heat as a function of temperature or time. Here we are considering temperature, and that time we are heating at a particular heating rate. And if we try to see a pure metal DSC pattern, DSC trace, we would see that DSC trace would look like, when it melts, that time it actually is a endothermic reaction. So, you would get a plot like this, it absorbs heat. Now, if this is my exo heat, then this is endo heat, so at lower side, and this would be my melting point, and the area under this graph is nothing but del H m. Fine. So, this is a DSC graph, we can easily calculate this. Now, since we know this value, can we make use of this particular value while calculating del H T liquid to solid transformation at any temperature below Tm? So, that means at this point, from this point if we start, it will be all liquid, and then gradually it is following this path. And if we take the temperature below, keeping liquid as liquid without solidification or crystallization, then I can reach to this point, and if we hold that particular liquid at this temperature, then there is a possibility that it can go back, because I see that at that temperature I have a lowering in free energy. So, spontaneity is there. Now, then these value I have to calculate. I can simply calculate by difference on Cp of liquid and solid, and then get the value here. But since it is a state function, we can also calculate using this particular value into our consideration. How we can do it? So, if I try to give a notation, so this is HA, this is HD, this is HC, this is HB, let us say. So, at those points I have those enthalpy values. Now, if I try to find out the difference between these, so actually I am trying to find out AD. So, that means I am trying to find out HD minus HA. So, when I try to find out HD minus HA, so that means I am taking this path. But since the state functions are path independent, so I can also get this difference if I start moving this way. So, let us say I start moving this way. So, now if I go from here to there, from there to there, and then from B to A, and then I see the difference, it will give me the same difference. So, if I do this particular route, so then it would be DC plus CB plus B A. Now, if I put it in terms of H values, so H C minus H D plus H B minus H C plus H A minus H B. Now, this is related to CP solid. So, I can also write, so that means from T1, this is my T to Tm, T to Tm, Cp solid dt plus this is nothing but del H m, then plus Tm to T. So, that means Tm to T Cp L dt. I can write this way also. So, then if I take this particular term, I can put it this way, del H m plus minus T Tm Cpl. I reverse this position of temperature dt plus Cp S dt T Tm. I can just make little adjustment, I will get this. Now, this one we can, I just remove this part, then this becomes del H m minus T Tm Cpl Cps dt, and this is nothing but, if this difference is del H T, so this becomes del H m minus Cpl minus Cps dt. So, this finally I can write del H m minus T Tm del Cp, since it is a solid to liquid, so I can put liquid to solid, okay, dt. So, I get this information, fine. So, now del H T. So, it is basically liquid to solid transformation, fine. So, now if I get the expression like this, now there is one more term which is del S liquid to solid. I should, if I follow the same procedure, I would get so now I do get the information of del S liquid to solid and T del S liquid to solid, and I get two expression. This is one expression, this is another expression. Since I know del H m, I also would know del S m from experiment, and this is experimental quantity. So, I do get these two parameters, and I have to only do this particular thing. So, this here I just replace those del S, LS, del H and del S term, and T I know where I would like to do my experiment, and rather where I would like to find out the driving force, which is free energy difference. Now, if I take that particular thing and put it there. So, I just remove this part here. Let me remove this part. So, I will get del G liquid to solid T equal to del H m minus T T m del C p liquid to solid dt minus T del S m plus T sorry, there is a small change here, there should be a temperature here, okay, because del S is this. So, I just forgot to put this temperature term. So, this is this into dt. Now, since this is very easy to find out from experiment, which is the DSC, this is also easy to find out from DSC, but the difficulty is to find out this value. Now, we assume that the liquid remains liquid below melting point, but this is against to our actual experimental evidence. We have seen that once the liquid is taken below melting point, it solidifies, that means it becomes solid. But though you will later come to know that these liquid can remain liquid over an entire temperature below, over a very large temperature below Tm, and the reason for that would be simple homogeneous nucleation. We will talk about the nucleation term later, but for your information, let me tell you the liquid water, okay, we have seen that once we take it to 0 degrees Celsius, it solidifies. But actually the liquid water can be maintained liquid even below minus 40 degree below the 0 degree Celsius. So, that particular undercooling, we call it undercooling, is possible if we can allow homogeneous nucleation in liquid. So, that time we can maintain liquid as liquid below melting point, and we can easily find out what is the Cp. People do calculate Cp of liquid like that. But since those experiments would be very, very expensive as well as very elaborate experiments, before we try to find out Cp, let us see whether we can have little bit of assumption, which will be a little kind of unjustified assumptions. But initially let us take that those unjustified assumptions, and later on we will take more justified assumptions, and we will see what is the difference that justified assumption would create over the unjustified assumptions. I would simply consider those assumptions, those crude assumptions. For example, the simplest assumption could be, if we do not have del Cp value, it is very easy to find out Cp of solid, but it is very difficult to find out Cp of liquid below melting point. So, we have to take some value of this particular del Cp. So, if I assume, let us assume a very simplistic value to this, let us assign some value. So, one assumption could be, if del Cp liquid to solid is constant. Now, we take constant value, that means it does not change over the entire temperature gamut, temperature range below melting point. But then next question is, what would be that value? Okay. So, then it is a problem. Now, the next crude assumption could be, if we can take it to be 0, which is, let me tell you, this is a very crude assumption. Okay. But still, let us see whether these assumptions would create any problem for our further calculations. Okay. So, now if we take this to be 0, then this term as well as this term goes to 0. So, we are left with this term and this term. So, now if we try to take the del G liquid to solid, then it is going to be del Hm minus T del Sm. Now, if we see this particular diagram, we see that at melting point, this value is 0. So, if that is 0, if we take T to be Tm, then del G liquid to solid is basically del Hm minus Tm del Sm, and this is at T equal to Tm, which is nothing but 0. If that becomes 0, so then I can write del S m equal to del Hm by Tm. So, I convert everything in terms of enthalpy of melting or latent heat of melting or solidification. So, now if I know this particular expression and if I replace that here, what do we get? So, I replace it. Now, if I replace it, then it becomes del Hm T m minus T by Tm, which I can simplify as del Hm del T Tm. Fine. So, now final expression is this, where this is nothing but undercooling. This is nothing but undercooling. Okay. See, this undercooling term, if we see that undercooling is directly proportional to the driving force, because these two terms are constant for a particular metal. So, that means this is proportional to driving force. What does it mean? This is a thermodynamic quantity. So, that means if this is proportional to driving force, then this becomes also a kind of thermodynamic quantity. I think let us stop here. We will continue in our next lecture. Thank you very much.